last time? Last time we talked about the Weierstrauss P-function, which let me write it like this: a sum over all lambda in lambda, 1 over this forbidden square averaging, which we make okay by putting out 1 over lambda squared here. And as long as we sum all of these terms, it's okay, with the understanding that, I mean, this is a non-standard way to write it, where I'm interpreting 1 over 0 as 0. The more standard way of writing it is 1 over z squared, the term with lambda equals 0, plus all the other ones, the non-zero terms of this same thing. Okay, we saw that this was elliptic. Lambda, of course, is generated by some omega 1, omega 2 with omega 1 over 2 or 2 over 1, whatever, not real. This is elliptic, and all elliptic functions on lambda, or with respect to, I think with respect to is better than on, with respect to lambda, are rational functions of p and p prime. So that was one reason to want to study this function. And the other reason to want to study this function is actually it parametrizes elliptic curves. So p, we showed that p prime of z squared minus a cubic in p, which was p minus e1 times p minus e2 times p minus e3 is equal to p prime squared, where e1, e2, e3. So p at this center, at these half, if this is my lattice, just reminding you what we did last time, these half lattice points, w1 over 2 was e1, p of w2 over 2 was e2. Of course, it doesn't matter which one is which. And the center point was e3. Okay, so we parameterize elliptic curves. This is why a function like y squared is equal to a cubic in x is an elliptic curve with distinct roots for the cubic. And if you're interested in understanding elliptic functions that arise as inverses of elliptic integrals, which arise when you study arc lengths of ellipses, then these are the functions you are sort of naturally 100 years later led to. Okay, let's get a little deeper into our understanding of the Weierstrauss P function, and we'll get to some really crazy stuff. Maybe I will go a little off the deep end and tell you about things like Fermat and BSD and so on. But first, there's a nice, Poincaré says one more thing. Should I show you that we haven't discussed? Stein, Shikarchi. Poincaré, we were just here somewhere. Poincaré says one more thing about these. He's got this great quote. We've understood almost all of the quote. Here it is. We're back to the quote. In Weierstrauss' system, instead of those three functions, we have the one p. It's the simplest of all, having the same periods. So it's one function, so of course it has the same. It has only a double infinity. And finally, its definition is so that it does not change when one replaces one system of periods by another equivalent system. So let's see if we can understand what that means. So an equivalent system is alluding to the fact that we can study the space of lattices. And I could have used W1 and W2 as the generators, as a basis, as an integer basis for the lattice. But I also could have made any change of variables. You see, if I replace W1 and W2 by some integer, by some invertible integer linear combination of W1 and W2, it'll generate the same lattice. In other words, if you think about, I mean, yeah, okay, I think that what I said is clear. Replaced by an invertible Z linear combination, In other words, let's be explicit here. Something like W1 is replaced by A W1 plus B W2, and W2 is replaced by C W1 plus D W2. In other words, this is the same thing as just multiplying W1, W2 by the matrix. I hope I wrote this right. AB will be that, and CD is that. Okay, I'm writing it like this, so it's a column vector or something, transpose. Okay, where A, B, C, D are integers and invertible, and this matrix is invertible in the integers. If that's the case, then the lattice, so the lattice lambda can be generated by W1 and W2, can just as well be generated by, let's call this matrix gamma. So this is also the lattice generated by gamma, the gamma of W1, W2. Hopefully, I'm abusing notation in a lot of different ways, but hopefully it still makes sense to you. For any gamma in the group gamma of these invertible Z-linear combinations, which has another name, SL2Z, exactly. So the fact that this is invertible in the integers is actually GL2Z, because the determinant doesn't have to be 1, it could be -1, and that's still, so in this case, it's GL2Z. But in a second, we'll want to restrict to SL2Z, as we'll see. Okay, so any invertible, integer invertible. So these are, what are the possible determinants of invertible plus or minus 1? So the only difference between GL2 and SL2 is plus or minus for the determinant. Okay. So Y is the definition of the Poincare of the Weierstrauss P function invariant under the choice of generators for the lattice was just a function of the lattice. It doesn't care which generators you put in. So it's sort of obvious. This last thing that he said is obvious, that you don't, it's not the, it's like if you were thinking about the ellipses, and instead of having one parameter, you had multiple parameters, and those multiple parameters changed the way that you, that's what happens with this sine amplitude function, this Sn and Cn and Dn. These functions really depended in essential ways on what was being used to generate the lattice. Whereas here, it's just a function of the lattice itself. It doesn't care that what choice of basis you make. Any choice of basis will lead to the same lattice, and so the P function is invariant. Does that make sense? Now, there's something even more that you can do. You can reduce, instead of having 2 degrees, this looks like we have 2 degrees of freedom, 2 complex parameters, W1 and W2. We can reduce matters even further. Note, so here's an observation. If I take any, let's see, how about U as a complex number, invertible complex number? What happens if I take P and I scale and I multiply the lattice, every element of the lattice by U? In other words, if I had the original lattice, here's the original lattice. I don't know why I'm drawing the fundamental domain. The lattice is the set of lattice points, wherever they are. Okay, this is horribly drawn, but you get the point. I multiply them all by U. So U has some argument, some angle. So I rescale by U, and it has some absolute value, right? So I take the whole lattice, I rotate it a little bit, and I stretch it a little bit. So I get a new lattice. Let's give this a little color. So I get some new lattice, which has been rotated and scaled, but otherwise is the same. In other words, like the angles from the origin are the same. I don't know what a good way of drawing this is. Okay, it's clear what's happened, right? Everything gets scaled and rotated. That will change. That will change P, because we're summing over the lattice. I mean, if you sum over the lattice and you're multiplying each lattice point by a number U, that's going to change things. But if you also multiply Z by the same number U, then how will P change? So implicitly, there's a lambda here. But if I change lambda by multiplying every element in the lattice by u, and I multiply z also by that same u, then a factor of 1 over u squared comes out. Exactly. So if I multiply z also by the same factor u, then that's 1 over u squared times p at the original lattice at z. And in this way, we can reduce studying p on any lattice to studying p in a particular kind of lattice, or a normalization for the space of lattices. So we'll say that two lattices are equivalent if one is just a rotation or a rescaling of another. Two lattices thinking. So by this transformation, thinking of two lattices as being, let's say, having the same shape, as having the same shape if one is a rescaling and rotation of the other, we can reduce the study of these things to what? Well, let's say that the argument of, let's say this one's W2 and this one's W1. So the argument of W1 is greater than the argument of W2. Just otherwise replace which one's which, right? Which is an invertible matrix in the integers. So if I divide everything by W2, so if I replace the W1, W2 by dividing everything by W2, I get W1 over W2, comma 1. It's the same thing as what we were doing before with projectivizing this action. And if we do that, then this multiplying by W2 means reducing the angle by W2. So let's do this in a third way. Reducing the angle, dropping this down to W2, and then rescaling by the amount, by the length of W2. So that shrinks W2 to have length 1. It's as if we pretended W2 was 1. Now W1 also gets rescaled and reshrunk to some point that's traditionally called tau. So if we define this thing to be tau, let me go back to that. The fact that W1 had a larger argument means that tau, can you tell that that's a tau? Let's call this tau. Tau is in the upper half plane, has positive imaginary part. Okay, so we can think, so in this way, we can think of p as a function of lambda. I mean, it's not a well, it's a function of z, but it has lambda as an implicit parameter. We can think of this by this transformation as just being a function of tau in the upper half plane, being the parameter, like the eccentricity, and z is the variable in which it's holomorphic. Does that make sense? So by this, I mean, again, 1 over z squared plus a sum over all of the lattice points in the lattice generated by tau comma 1, except for the 0 element. And then the same thing, 1 over z plus lambda squared minus 1 over lambda squared, these taken together so that the series converges. Okay, does that make sense? There's more to be said about this tau, but let me save that for just a minute. The next thing I want to try to understand, so this was reducing the question, so the space of lattices, we can think of, at least at first, as being parameterized by this tau in the upper half plane. But of course, that's there will be other points that are equivalent to tau in the same way that lattices are equivalent to one another. Should I talk about that now? Let me come back to that. Before I do that, I want to do one more thing, which is I want to understand this P function has a very interesting Taylor expansion near 0. Okay, so come back. I'll put a little star here. Come back to the space of lattices up to homothety, up to this this rescaling and rotation. They have the same shape up to homothety. So that's this rescaling and rotation has a fancy name. Let me come back to that. First, let's study Taylor series of P tau or P lambda of Z near Z equals 0. Okay? And we're going to see something rather interesting happen. Why would you think to do such a thing? Well, it's understanding Taylor series. It turns out that understanding Taylor series and Fourier series of functions that have these symmetries, this periodicity, leads to, I don't know why a priori necessarily you would want to do such a thing. Yeah, there's a variety of reasons. I'm cooking it up. Yeah, let's see what happens, and you'll see why this is a natural thing to do. There is a reason I claim that it's easy to justify. Maybe, okay, let me shut up and let's calculate. So near Z equals 0. So what do I mean by near Z equals 0? Well, for example, okay, I'm putting already one of the basis vectors at 1 and the other one is tau, but the lattice is everywhere. The lattice is all around, but there's some like shortest distance. And so shortest distance to the lattice point, to the lattice. And so if I'm less than, let's say for all lambda in the lattice except 0, Z minus lambda, or just Z over lambda. Z is so small that Z over lambda is less than a half. Okay, for larger lambda, this is obviously going to be small as lambda gets farther out. The closest I want to be less than half of the distance to the nearest lattice point. Okay, then what can we say? Well, let's look at P again. P of Z is equal to 1 over Z squared. So we have already this order 2 pole, and I want to know what the other terms are. There's a minus 1 over Z plus A of 0 plus A1Z plus A2Z squared, and so on. I want to work out what these Taylor coefficients are. Some of them are very easy to work out, actually. Is there something we know about P? It's even. Exactly. P is even. And so what does that mean about
the odd coefficients?
The odd coefficients are gone. Okay. So the odd coefficients are gone. We will only see the even coefficients, but let's try to work out exactly what those are. Okay. So how do we work out what that is? Well, P of Z, again, let's put the definition, which is what I was starting to do, is a sum over lambda in the lattice. And then we have this 1 over Z plus lambda squared minus 1 over lambda squared. And we can write here Z plus lambda or Z minus lambda. It doesn't matter because lambda is symmetric about the origin. A plus lambda has the same thing as a minus lambda. And let me pull out, because Z over lambda will be small, I want to write this. I want to pull out a lambda squared from here and put a Z minus Z over lambda, and this over lambda will be a 1. Okay, so in fact, the 1 over lambda squared can be pulled out of everything. So we will need to know what the series 1 over 1 minus alpha quantity squared is, where alpha is less than a half in absolute value. You see that this is 1 minus alpha, where alpha is Z over lambda. So wait a second, I know what this series is. If I just have 1 over 1 minus alpha, what's the Taylor expansion of that? Yeah, exactly, the geometric series, 1 plus alpha, 1 alpha squared, alpha cubed, and so Okay, so if I differentiate both sides of this, I get negative 1 minus alpha to the minus 2, chain rule minus 1. And if I differentiate this, I get 1 plus 2 alpha plus 3 alpha squared plus 4 alpha cubed and higher order stuff. Okay, so in fact, 1 over 1 minus alpha squared is a sum over L greater than or equal to 0 of alpha to the L. The coefficient of this is L plus 1 by the looks of it. You buy that? And this converges absolutely and uniformly as long as we're staying away from the poles. So certainly if alpha is less than a half, then this is a nice, absolutely convergent series. Converges absolutely and uniformly on this set. Less than or equal to, doesn't matter. Okay, so that's what I'm going to do here. So I have my 1 over z squared out front. I have a sum over all lambda in lambda. There's a factor of 1 over lambda squared. I can actually pull that out of everything. And then what will be left, the minus 1 is from that term. And what's left is a 1 minus z over lambda squared. I know how to expand that. So this is a sum over L greater than or equal to 0, L plus 1 times z over lambda to the L. Does everybody buy that? So far, so good? Let me give you a second to finish writing. Okay, what's the term L equals 0? It's 1, so that's going to cancel that. And we start at 1. That means there is no constant term. There's no term with z equals 0. So we've worked out one of the coefficients. A0 is in fact 0. Okay, so that's this thing that makes it converge by killing off the constant, what would be the constant term. Does that make sense? Okay, what else do we have? So let's reverse orders. We want to know what the power of z to the L is, right? Where the Taylor expansion is now sitting here. We just have to unpack it. So this is a sum, 1 over z squared, no 1 over z, no z to the 0. And then what else is here? So it's a sum plus a sum as L ranges from 1 to infinity. There's a z to the L. There's this factor, L plus 1. Okay, that's there. And what's left over is a sum over all the lattice points. And this is the fascinating function, a sum over all the lattice points of what? 1 over lambda to the L plus 2. Does everybody see that? This function has a name. Does anybody know what this series is called? This is called an Eisenstein series. This has a name. So the Eisenstein series of weight k, which is written like this, E sub k of tau. So now I get to speak of tau being, this depends on the lattice, but it does not depend on z. So it's not it's a constant as far as the Poincare series. As far as the Weierstrauss series is concerned, it's not a function of z, but it is a function of the lattice. So we're trying to understand, like at the moment, this is P of z, right? There's a 1 over z squared term. There's nothing. There's a z to the L plus 1. How does this actually depend on lambda? Its only dependence on lambda is through the Fourier coefficients, the Taylor coefficients rather, the Taylor expansion. And the Taylor coefficients, the way what this is, so this thing will be E sub L plus 2 of tau, where tau is the tau of the lattice. So what is this? It's exactly what's here. It's a sum over all the lattice points except for 0, 1 over the lattice point to the power k. That's the standard definition. And of course, this is the Eisenstein series with k replaced by L plus 2. All right, when does this converge? The series converges. Let's make this even more explicit. The lattice lambda, lambda tau, I remind you, is generated by tau and 1. So this is the same thing as saying we're going to sum over all pairs m and n of integers except 0, 0. We're taking out the 0, 0 term. And lambda is m tau plus n raised to the power k. Okay, just to be completely explicit. So again, we have a sum over pairs of integers, m and n. Tau is in the upper half plane. I remind you that tau is in the upper half plane. The imaginary part of tau is positive. So there's no poles. And this, in fact, is a holomorphic function of tau in the upper half plane, because this series will converge. Okay, where it converges. So let's see, where does it converge absolutely? For k, for what values of k? Exactly, strictly greater than 2. But actually, we want this to be a holomorphic function. So, i.e., k is an integer, k is greater than or equal to 3. Okay, which, by the way, are we in that realm here? L is at least 1, so L plus 2 is at least 3. Wait a second. If k is odd, then whatever plus value of lambda I have, I also have a minus value. And they'll all get added together. And k is odd, so the Eisenstein series ek of tau is 0, is identically 0. We knew that already. We knew that already because that has to be the Taylor coefficient of p, and p is an even function. So this is why the odd values here cancel off, and the only L's that occur are actually even L's. So in fact, we could write p. I'll keep the lambda here, although maybe I should already be putting a tau here. P sub tau of z. Let me write this thing out as 1 over z squared plus a sum. Maybe instead of L, I'll write I'll replace L by 2k. So this is k at least 1 of z to the 2k, so that it's clear that only even powers appear. There's this constant 2k plus 1. And then what's here is the Eisenstein series at 2k plus 2 of tau. And again, the only dependence on tau is there. So far, so good. So now we have this fascinating function, e sub tau of k. And notice, again, I said this before, as long as k is at least 3, which actually 3 doesn't do anything, as long as k is at least 4. If it's 3, then the Eisenstein series vanishes, so there's nothing to say. If k is equal to 4 or higher, but again, 3 would have been enough, this series converges, absolutely and uniformly on the region imaginary part of tau is at least some fixed constant. If you have at least some fixed constant here, then this series will converge uniformly on that. And so you get a holomorphic function. So this Eisenstein series is holomorphic in tau as tau ranges over the entire upper half plane, because it's holomorphic for any delta greater than 0. It converges uniformly. Okay. So now let me ask again about the space of lattices. two lattices are completely equivalent. P really doesn't change at all, not just up to homothety, but completely equivalent. If I make a change of variables, if I change W1 and W2 by an element of GL2Z. Now, one thing that it can do, okay, so consider replace 1 tau by gamma times gamma is ABCD by gamma acting on tau and 1. Okay, so again, this is ABCD times tau 1, which is A tau plus B, and then C times 1, C tau, I can do my matrix multiplication, I promise, times D. Okay, so that won't change the lattice at all. These two will generate exactly the same lattice. These two vectors will generate exactly the same lattice. But remember, we want to think about lattices up to homothety. So we want to divide through by W2. So this is similar to, I'm going to divide both sides by W2. So what's C tau plus D divided by C tau plus D? Thank you. 1. And what happens to the other basis vector? It turns into A tau plus B over C tau plus D. We are again seeing this fractional linear transformation. Okay, so if we want to understand what happens to these Taylor coefficients, then we can replace, so what happens to EK of tau when tau is replaced by this fractional action, A tau plus B over C tau plus D. Is this a good quiz problem, or is this a little too hard? I think it's a little, let's do this together. It's not hard at all, but I haven't given you the idea. Yeah. Let's do it together and then you'll see. Okay, so again, what is EK of A tau plus B over C tau plus D? Okay, so EK of anything is this sum right here. So I'm just going to write that sum again. So it's a sum over all integers m and n, except for 0, 0, and 1 over m tau plus n to the power k. And tau is replaced by A tau plus B over C tau plus D. So far, so good. Let me pull out a factor of C tau plus D to the K. So this has a factor, C tau plus D to the K. And what's left over is a sum over Mn in Z2, 1 over, so it's like multiplying the denominator by C tau plus D to the minus K. If I pull this out, it comes out with a minus K, which is the same thing as putting it in the numerator. So I've pulled that out. So that's an M times A tau plus B plus N times C tau plus D. All that to the K. Hopefully you believe it. Okay, so far so good. So there's this C tau plus D to the K. There's a sum over M and N. And let's group the tau terms. The tau terms are MA plus NC tau plus, and what are the constant terms? MB plus ND. All that to the K. It's a very complicated sum. Or is it? Tim, why not?
You could probably with both of those just reproduce everything in V2.
Exactly. Exactly. If I write this as U and this is V, then all we've done is we've taken our MN multiplied by ABCD, or maybe not ABCD, ACBD. and gotten a u and a v, a pair of integers. But this is an invertible transformation. So as m and n range over all pairs of integers, of course, not zero. Let me put a star there, not zero. As m and n range over all non-zero pairs of integers, so does u and v. So this whole thing is a factor c tau plus d to the k. And what was this? It's the Eisenstein series all over again, ek of tau. Okay. Now there's one little caveat. The one little caveat is this point, this a tau caveat is that a tau plus b over c tau plus d, I'll leave this as an exercise in the interest of time, is in the upper half plane if and only if the determinant of a, b, c, d is positive. So in our case, +1, since we're thinking about integer entries. Okay, if the determinant's negative, then tau, it's like replace tau by negative tau. Yeah, that's a great transformation, doesn't change the lattice, but now tau is no longer in the upper half. Okay, so that's why, so the theorem that we just proved is that for all a, b, c, d in SL2Z, not GL2Z, because we don't want to leave the upper half plane, ek of, I'll call this gamma tau, gamma acting on tau by fractional linear transformations that we've seen already, is equal to c tau plus d to the k. That k comes out, and then ek of the original tau. Functions that have this property have a name. They're called modular. So if the way that you change under a fractional linear transformation by some congruence group, or in general, some arithmetic group, is that some factor comes out. So it's not automorphic. Automorphic would be if it doesn't change at all. We've seen automorphic functions already or not? I can't remember. Have we seen functions that don't change at all, that are just invariant under some group action? Have we had the word automorphic? They change into themselves. So this function, it's not true that ek of gamma tau is equal to ek of tau. But it has this, the way that it modifies itself is the way that it's modified is by this factor c tau plus d. So this is called, i.e., ek is a modular form. Definition by example is a modular form, and this parameter of weight is called a weight k. Say it again. Well, even functions you could say are automorphic with respect to the group z plus or minus 1. Exactly. Yeah. No, but okay, yeah. This is a much more interesting group, of course. Yeah, usually we're interested in non-abelian groups when we speak of automorphicity. But anyway, yeah. So this is a modular form of weight k. So in other words, what ek yeah. I was about to say what ek does on a fundamental domain determines what it does everywhere, but it's not invariant under this transformation. It has this factor. Fine. So we've discovered, so let's go back. Where are we? We tried to understand the Taylor series expansion of the Weierstrauss P function near zero. It has this double pole. It has no constant term, and the z to the 2k terms have this explicit constant times this fascinating function, an Eisenstein series. Okay. Here's something else we can see from this expansion. Again, let me just write the expansion out. P of z is 1 over z squared. Then there's what's the z squared term? It's it's times 3, right? Yeah, the z squared term has times 3. And when k is equal to 1, this is E4. whoops, too far. Hello, way too far. Times 3e4. And there's a z, not cubed, but z to the fourth times 5e6 and higher order terms. Okay, so what about p squared? So if I square this whole series, I take both sides and I square it. What do I get? Well, let's see. If I square the 1 over z term, 1 over z squared term, I get a 1 over z to the fourth. Can I get a z to the -2 term? I'll only get even terms. P squared is also even. Will I get a z to the -2? I have a z to the -4 term. Will I get a z to the -2 term? I don't see how to make that. Will I get a z to the 0 term? So let me write 0 over z squared. Where's my z to the 0 term? It's going to be this thing times that thing. And it's going to happen twice. So that's 2 times 3 times e4 times z to the 0. Okay, how about a z squared? Let's do one more. How about a z squared? I think when I square this, I get a z to the fourth. So the only way I can get a z squared is by multiplying these two together. So that's a 10e6 z squared, and then higher order terms. So what about p cubed? So I'm going to multiply this whole thing by one of these. So I have a 1 over z squared and a 1 over z to the 4. That gives me a 1 over z to the 6. We knew that p cubed had this order 6 pole at 0. Can I get a z to the 4th? Is it possible to get a z to the 4th out of this? That's either a z to the 4th times a constant. No, I don't think I can get a z to the 4th. Can I get a 1 over z squared? Yes. This times this is a 1 over z squared. Is there anything else that's a 1 over z squared? This times 1 over z squared times a constant is also 1 over z squared, right? So the coefficient in front of 1 over z squared is I'm getting a 3e4 and 6 more e4s. So I get a 9e4 over z squared. Does that look right? Okay, and let's do one more coefficient. What's another coefficient? I can get a constant coefficient. One constant coefficient is there. And I don't get this twice because I'm not squaring things. So one constant coefficient is there. So that's a 5e6. If I have another constant coefficient, I guess I have another constant coefficient there. That gives me a 10e6. So I get 15 e6s times z to the 0. And then plus higher order terms. Another nice thing so let me take off the squares here. Another nice thing about having the Taylor series is that we can differentiate term by term. So we can write down what p prime is. What's the derivative of this term by term? Z to the -2, the derivative is -2z cubed. How about this? What's the derivative? Z. How about this one? Derivative? (20e6 z cubed) and higher terms. So what if I square this? You see what I'm doing? Maybe this is a good quiz. We've had enough examples of this. Take a second and square this out and tell me what series you get. I only want 3 terms. Why am I computing p prime squared and p cubed? You already done? Okay, not that hard.
You said you should just teach me.
Yeah. So you should get a 1 over z to the 6th term. I think I see a 1 over z squared term. And then constant term. Yeah, okay, it's not that hard. But other people are still writing. So any guesses on why we're computing this?
You already have an expression for what we're doing.
Yes. We do already have an expression relating p prime and p. In fact, relating p prime squared and a cubic in p. I want to find another expression for the same thing. Oops. Shall we do it? Okay, it's not that bad. So if I square this term, yeah, together now, 4 over z to the 6. How do I get the next square is going to give me a z squared. How about this cross term? Gives me negative 12, but there's 2 of them, so negative 24. Did you guys get that? Negative 24 E4 times z to the minus 2. That's interesting. And then let's get one more term. I think the next smallest term will come from the 2 z cubes. So I get a negative 40. So is it negative 80? E6 times the constant term plus higher order stuff. Does that make sense? So if I multiply p cubed by 4, so 4 p cubed, just to match that first coefficient, I get a 4 over z to the 6 plus 4 times 9 is 36. 36 E4 over z squared, and 15 times 4 is 60. E6 times z to the 0 plus higher order terms. And so if I subtract, so here I have p prime squared minus 4 p cubed. What's left here is a negative 50, 60, negative 60 E4 times 1 over z squared. And then a negative 140 E6 times a constant. So if I take one more copy of P3, if I add, not P3, just P. If I add 60 E4 P, then that will kill off this term. I mean, there's higher order terms. That will kill off this term. And this is an elliptic function with no poles, and hence a constant. What constant is it? This is elliptic of order 0, implies constant. What's the constant? Yeah, send z to 0. Send z to 0, this side goes to, this is the limit as z goes to 0, as z goes to 0. So this is the constant. So what we've proved a kind of interesting theorem. P prime squared is equal to, I'll move these things back to the side, 4 p cubed minus 60 E4 p minus 140 E6. We knew this theorem, but in another terminology. In fact, the other terminology was that P prime squared was exactly. Which means we can express the Eisenstein series in terms of E1, E2, E3. So if I multiply this cubic out, let me multiply this cubic out. This is a 4p cubed. Why am I having trouble with my p? What's the term in front of p squared? It's 3 minuses. So it's minus 4, E1 plus E2 plus E3, p squared. What's the term in front of p? I have to multiply 2 of these and 1 of the p's. So I guess that's a plus 4, E1, E2, plus E2, E3, plus E3, E1 times p. And what's the constant term? Now I have 3 minuses, so minus 4, E1, E2, E3. What's the sum of the e's? Zero. The sum of the e's actually has to be 0. Exercise, find another reason why that's the case, because there's no quadratic term here. There's no p squared term here. What is the sum of the pairwise products of the e's? Kaylee, something you don't like?
I thought you defined these in terms of the generators of the box
Yes.
in a way that should not come to zero.
Well, this is a crazy fact. The way we define the e's is the value, each of the e's is the value of p at the half lattice points.
Okay, great. So you value it by
So even though they're all distinct, the sum of the 3 has to be 0. Think about why that would have to be the case. But we proved it by this crazy, I don't know if you want to call it coincidence or evaluation, whatever. Say it again. Well, where we're evaluating them is all in the first quadrant. Where it's E1 is the value of P at W1 over 2. Yeah. It's not. Yes, it's not W1 over 2, W2. It's the evaluation of P at those 3 points. These distinct E1, E2, E3 that are all distinct, but the 3 sum to 0, actually. What about the pairwise product? Yeah, well, there's a 4, so minus, what is it? Minus 15 E4. And how about the triple product? Did I get this 140 right? Yeah, 140. Yeah, it's 140. Oh yeah, I have plenty of 2s. I can divide it by 2, 70 divided by 2, again, 35, E6. That's kind of funny. So, all right, what can I tell you about this? So we see this identity from another viewpoint. You start seeing these crazy identities on top of identities. The more you mess around with this stuff, there's like so many weird coincidences and funny things that start to happen. So here's what happened. There's a little observation in the mid-80s, which was the following. So if you give me an elliptic curve, given an elliptic curve, something like y squared equals x cubed plus ax plus b, with a and b rational. It turns out that if you want to know, so this is the elliptic curve E. Okay, again, over the reals, E of R means put real values for x and y. You get some, we discussed the shape of this thing. It's supposed to be invariant under y goes to negative y. So it's that doesn't have a name, does it? It's like even in y. It's not a horizontal evenness, it's a vertical evenness, whatever. So this is the real points. Inside of it, there might be some rational points. There might be some rational points, rational solutions to the curve. There might be finitely many, there might be none, there might be infinitely many, it turns out. here's a crazy thing. This set of rational points actually has a structure of a group, an abelian group, a finitely generated abelian group. It turns out that this is a finitely generated abelian group. Does anybody know how to get, if I have 2 points, let's say P and Q, how do I get the sum of P and Q? You've seen this?
I've seen it before, but
Would it be like the line goes through?
Exactly. It's the line and chord method. So line going through it intersects at another point R, and we define P plus Q plus R to be 0. So there's a point at infinity in the curve. And so the sum of P and Q is actually this point, which would be negative R. So this point is the sum of P plus Q. If we define P, it turns out that this is what you have to do for the addition to be to satisfy the group laws.
You know that this R will be rational.
So here's the thing, if P and Q are rational, then solving, is that a square? Oh my God, and no one's stopping me? This is a cubic. So if you give me 2 rational solutions to the cubic, the third one's also, with rational coefficients, the third one's also rational. Okay, so you have to prove that this group is associative. That's the sort of the hardest part. It's commutative because we defined it in terms of if I replace P and Q, it doesn't matter. It's still the same line. What about P plus P? Yeah, well, if P is vertical, then it's on the line of infinity. But if P is just some other point, then it's the tangent line. That tangent line, because this is a cubic, that tangent line will eventually cross somewhere. And then again, the flip, the negative of that will be 2P. If this is P, then up here is 2P. Okay. The identity element, very good. The identity element is the point at infinity. So if you take P, if you take any P, and you draw the line through P and the point at infinity, then you get this point, and you need to take the negative of that point to get the sum, so you get back to where you started. So the point at infinity is the identity. You need this point at infinity. Everything should be done projectively, of course. Okay, so you have this finitely generated abelian group. Well, finitely generated abelian groups are completely classified, right? There's some torsion part. There's some finitely generated finite abelian group, some Z mod NZ cross Z to the R. And the R is called the rank. This is there are several ranks. So this is the algebraic rank of the elliptic curve. Then there's something else that you can do. If you're looking for rational solutions, if you have a rational solution, you'll have a solution mod P. So you could look at how many solutions there are in an E, not over Q, not over R, but over FP, the finite field on P elements. And it turns out that this number, so let's call this NP. So again, these are rational numbers, but as long as I stay away from the denominators for P different than the denominators of A and B, let's think of A and B as being integers. I'm looking for solutions mod P to this equation. I can find these solutions, and it turns out that the number of solutions, so let's just think naively, as X ranges mod P, then X cubed actually also ranges mod P. And about half of those numbers will be squares, and half won't. This will get into quadratic reciprocity, or yeah, there's some stuff that we haven't covered. So we need a little bit of number theory to really understand this. But basically, what you expect is that there will be P solutions. As X ranges, half of the values of X will be perfect squares, mod P. But then if you're a perfect square mod P, Y could be that square or it's negative. So it's half of P times 2. There's also one point, which is the point at infinity. And then, well, the NP is not equal to P plus 1. It's some weird thing that varies. So if we subtract off this AP is how much it varies. So you could define AP as n of number of points minus P plus 1. And a theorem of Hasse, this is the Riemann hypothesis for elliptic curves, is that this AP in absolute value is at most 2 root P. This is the Riemann hypothesis for elliptic curves. According to Weil's reinterpretation of the Riemann hypothesis in this setting. Anyway, this is also called the Ramanujan conjecture in general. Let me just throw another word in here, Ramanujan conjecture. Actually, I can explain what Ramanujan's conjecture is, I think. Let's see. I said I wasn't going to spend more than 10 minutes on this, but I'm just giving you a crash course on what's to come if you start studying these things. Please.
It sounds like a very broad statement.
Yes.
No.
No. This is a very, very broad conjecture, which in the very special case of elliptic curves boils down to this statement. And this statement was proved long before people understood what it meant in this more general scheme. So Taniyama, Shimura, and Weil. So this is the Shimura-Taniyama-Weil conjecture. Shimura-Taniyama-Weil. What's going on? The pen's falling apart. Weil conjectured that, okay, we haven't talked about the coefficients of the Eisenstein series. I don't have time to, let's take one little detour. Let me come back to this for just a second. So this Eisenstein series, if I replace tau by tau plus 1, that corresponds to the matrix 1, 1, 0, 1 acting on tau, right? Because this matrix is tau plus 1 over 0 tau plus 1. So that's just tau plus 1. That's just translation. If I replace tau by tau plus 1, what happens? I get CZ plus D to the K times EK of tau. And what is CZ plus D? That's a 0. It's hard to read. 0 tau plus 1. So this is 0 tau plus 1 to the K. So it's just 1. Okay. So EK of tau plus 1 is EK of tau. Tau is invariant under translation. But things that are invariant under translation have Fourier series. So this can be expressed as a sum over all integers of some coefficient. If I write tau as x plus iy, where y is positive, tau is in the upper half plane. So I have some coefficient, possibly depending on y. Oh, I see. I keep hitting this, this little button here. That's what's going wrong. Possibly depending on y, times e to the 2 pi I n x. That's the Fourier expansion in x. But actually, this function is holomorphic in tau. EK is holomorphic in tau, implies it satisfies Cauchy-Riemann equations. Cauchy-Riemann. And that means we can solve for what an of y is. An of y, I'll spare you the calculation, but because we know how it changes in x, we'll get a differential equation on how it changes in y. We'll solve that differential equation. That differential equation will be solved by e to the minus 2 pi ny. In other words, if I stick this in for here, then this and this together mean that there's a expansion, a Fourier expansion for e, which is some coefficient e to the 2 pi I n tau itself. Tau is x plus iy. This is these two things added together come exactly into tau. Now tau is in the upper half plane, and so we've seen this before. An actually has to be 0 for n negative. And in the book, you'll work, so this sum really goes from n being positive, some coefficients. And Stein-Shikarchi work out what this an is, and it's something like a let me not, you can work out explicitly, can be worked out, AN can be worked out explicitly in the case of Eisenstein series. But for more general modular forms, cusp forms, let me not say what cusp forms are. For more general modular forms, things of this nature, things that have this transformation law, those ANs are mysterious. Taniyama-Shimura-Weil conjectured. So what's the Taniyama-Shimura-Weil conjecture? I'm doing this all over Q, but of course you can do this over much more general settings. For any elliptic curve, for any rational elliptic curve, there exists, and you'll see why this is, well, I'll say why this is an instance of Langlands. They conjecture that for any such elliptic curve, there exists a modular form, F, a modular form, on some other group, not SL2Z itself, but some congruence group, and not of weight K, but of weight 2, in fact, such that the Fourier coefficients, or at least the pth Fourier coefficients, AN, AP of F, are actually equal to the APs of the elliptic curve. These counts, the Fourier coefficients match the counts of the elliptic curve. And this became known as the modularity conjecture. Put another way, there's a way to go from the prime Fourier coefficients to all the other Fourier coefficients. There's something called Hecke operators that we won't have time to go into. But Hecke says if you know the P values, the APs tell you the ANs for all n. So put another way, what this really means is you give me an elliptic curve. That gives me this counts, AP of E. Hecke tells us how to turn that into a series, AN of E. And then so I'll put that series into, so if I take a sum, AN times this E to the 2 pi I n tau, is this modular? You can make this function. The question is, does the function have the symmetry? Is this modular? Is this modular? Okay, that was the Taniyama-Shimura-Weil conjecture. Have I gone way too far? You ready for one more curveball? So in the 80s, Frey, a German mathematician, says if x to the p plus y to the p equals z to the p has an integer solution, has a solution, non-trivial solution, then you can make the elliptic curve y squared is equal to, let's use the ABC instead. If a to the p plus b to the p equals c to the p has an integer solution, p is a prime, of course, greater than 5 or something. We know from Wiles+Taylor theorem for small primes. Then when you make the curve, what is it? Am I going to come up with it on the spot? It's something like a to the it's something like this, x times x minus a to the p minus x to the b to the p. This has extremely weird properties. This elliptic curve, by this fact, will have extremely strange properties. And in fact, he conjectured, so he observed, Frey observed, that this looks like it won't be modular. Won't be modular. It doesn't, the symmetries are all off. And in fact, this observation was turned into a theorem by Serre and Ken Ribbit. So I should write Frey's name. I hope I'm spelling that right. Can someone check? So he observed that this won't be modular. So if you prove the Taniyama-Shimura-Weil conjecture, or at least it turns out it will be semi-stable for some subclass of elliptic curves. So Taniyama-Shimura-Weil implies Fermat's theorem. This was the state of things in the early 90s or late 80s by now, late 80s. And this is exactly where Wiles comes in. And so this is Wiles proves enough Wiles and Taylor Wiles. prove enough about the Taniyama-Shimura-Weil conjecture to conclude Fermat's last theorem. And now lots of other people have finished off Taniyama-Shimura-Weil over Q. So we know that every elliptic curve over Q is modular. And we have more, and people are still hacking away at other number fields and other settings. Okay, so this is an instance of Langlands. This is an instance of Langlands because Langlands predicts for all kinds of situations some modular automorphic object, a form or representation or this very complicated things happening. It predicts that when you make coefficient series, they have weird symmetries that you could not predict a priori. Well, that Langlands predicts. So it's like symmetries on steroids, symmetries on symmetries. The way I like to think of it is this. I'm going to give you a sequence, okay? Here's the sequence. 0, 1, 0, -1 over 3 factorial, 0, 1 over 5 factorial, 0, -1 over 7 factorial, and so on. You're going to make that into a series. So this is no constant term. So 0 plus z plus 0, z squared, minus 1 over z cubed plus 0 plus z to the 5th over 5 factorial, and so on. What is this thing? Sine. This is sine of z. By what rationale can you argue that this thing, if I replace z by z plus 2 pi, is invariant? How do you see that symmetry? You know it from sine. If I give you the modular function, so sine is like the primordial modular function. It's like the elliptic curve is giving us the coefficients, and we're trying to prove that what results out of that is itself modular. Now, the way Wiles, okay, let's not go into, I'm already over time. I promised you one more $1 million problem, which was the, I guess Fermat's not a $1 million problem since it's solved already, but Fermat, no. It had some numerical bounty, but again, it was before the Clay Institute started this $1 million problems thing. Now we have $5 million, but $3 million problems. Anyway, these APs, how can I say this? You're not supposed to be able to tell except for conic sections, these quadratic, remember we talked about these quadratic polynomials? I'll just say it in words. For quadratic curves, or in general, there's a more general setting for this. There's something called the Hasse principle, which says if you understand what's happening mod p for all p's, and really mod prime powers, and really in all completions, in all local fields, then you should understand what's happening in global fields. Global fields means Q. So if you want to find a rational solution to a quadratic polynomial equation, you should check, do you have a solution mod p and in the reals and powers of p? And that should give you, and there's lots of instances where that's a theorem, that implies that there's a rational solution. This is not true once you go to higher degree. So the Hasse principle completely fails, but these APs, which are local coefficients, they're only measuring the elliptic curve mod p. There's something called an L function, which we can't get into, but that L function may or may not vanish at the center of its. This L function is an analog of the Riemann zeta function. It has a functional equation. By the way, that functional equation is a consequence of the modularity. I mean, the mere existence of that L function, whatever. Whether it vanishes or not, and how much it vanishes as a holomorphic function at the center of this critical strip, should be measuring this. That's called the analytic rank. And the Birch+Swinnerton-Dyer conjecture is that the analytic rank is equal to the algebraic rank. And that's $1 million problem that we still don't. Okay, so let me not write any of this down. I just wanted to show you that this stuff is like intimately related to very, very modern questions at the forefront of research.